Yeah, let's start. Like today should be quite easygoing. Just kind of try to tell you the context of the area, and yeah, just ask question if there is anything. And yeah, so what I hope to tell you is like the history of the area, and some recent development, and then some other central concepts that I didn't have time to cover. Yeah. Okay. Okay. So, like, we can say that the thing from this class actually started since 1980, something like this year, which is like 40 years ago, something like that. Yeah. And so basically, before people know what is like or define what is expanded decomposition and hierarchy, there are some areas that motivate this. Yeah. And one is approximation algorithms. Like people start to care about like whether like checking if there is a sparse cut or not in the graph. Long time ago in like by the work by Layton and Rao. This is, by the way, the work that first show flow cut gap. Yeah. This is like since '88, and then like another.
Thank you.
Yeah, this is basically like the flow cut gap paper result that we studied is basically since this year, and there is another proof based for flow cut gap based on matrix embedding, which I taught it like several years ago that you can look up, but it's already also in this area. But basically, once people know what is like define the sparse cut, it kind of like it leads you to expanded decomposition in a quite natural way. Just keep finding sparse cut until you cannot find. Like just cut along sparse cut. That's then you get expanded decomposition. Okay. But another area is also spectral graph theory, okay, which we didn't talk about this at all, almost in this class, but actually expanders have another equivalent way to define it based on eigenvalue of the adjacency matrix, and it's interesting, and I also covered this in like another previous class, which you can look up again. But yeah, but there is another one which is graph minor theory. Yeah. So this is about like it's basically graph theory people. They don't care about maybe they don't care too much about algorithms, but they talk about graph structure. And to solve some disjoint path problem, they basically develop something like Welling set, or the thing that we say the set is expanding. That's the notion. Like when we talk about expanding set in this class, this is the notion that kind of developed in this area, yeah, long time ago. Also, distributed algorithm, they developed something called low diameter decomposition that we have seen, and that is kind of related or weaker version of expanded decomposition, but it appeared before expanded decomposition. So this is like it's kind of bring, like we kind of get to this point from motivation on many areas, yeah. But then it's only like 20 years ago that expanded decomposition is like explicitly, actually implicitly appear in literature, yeah. So this appears in the area of property testing. So what is this? This is like an area where like think like you have a big, huge graph, and you want to check if what is going on. How can I turn it off? Okay, I think it's gone. Random noise. Okay. Yeah, probability testing is some area where like you have a really huge graph and you want to test whether this graph satisfies some property in constant time. Okay. So you don't even want to spend time proportion to the size of the graph. You want to spend time constant to test if the graph is satisfy some property or it's really far from satisfying this property. Yeah. And it turns out expander is useful there. Yeah. But it's only in 2000 when Khanna, Vempala, and Veta define expanded decomposition, like explicitly. This is like where it first appear explicitly. Okay. And actually, this then three-flow specifier, which is defined by Recke, and people also call it Recke tree. Three-flow specifier is also defined long time ago. Okay? And the construction, which is based on boundary separator expanding hierarchy, BSE hierarchy, is already shown in his first work. Yeah. Right. And at that time, I think he got best paper for Fox or Stock from this work. Yeah. But and it's really surprising. Like, and this is supposed to be a surprising result that for any graph, right, there is a tree that basically approximates all cut structure. Okay, so that's really, really cool. Okay. And then it has found a lot of application. We see application to online multicut in the homework. There are many other applications which is like which is kind of nice, like that people use it to solve many approximation problems. Yeah. By the way, again, one open problem about three-flow specifier is that like we don't know the best quality. Okay. So the best known quality for three-flow specifier, we have actually learned the one with log cube. Okay. The best known is log square log n. The low bound is log n. For three-cut specifier, we learned the one which is log square. This is the one that is based on dynamic expanded decomposition, if you remember. Like we get BSE hierarchy with depth log n and expansion 1 over log. That's why you get three-cut specifier with log square. But the best known bar is this thing. Existentially, if you want polynomial time, it's this one. It's a bit worse. And the low bar is log n. So this is known. Okay? And by the way, one of the possible project is just to understand this too. Just read the paper, understand it, and explain it. Okay. So the paper is not so easy to read, and like, but by now, given the background from this class, it should be much easier for you to read these two papers than any other people. So, so if someone have a chance to like want to like giving exposition for these two paper would be good for our community. Yeah. Okay. But yeah, is lock-in the best? That's the good, really big open problem since 20 years ago. Okay. And then this expanded decomposition is defined based on a fixed node weighting, which is when A is degree. And actually, like most of the time when people has been talking about expander or expanded decomposition, they has been talking about this node weighting, degree node weighting. But it's actually until this work by Shekari, Khanna, and Shepard that they define kind of implicitly, not quite explicit, expanded decomposition for any node weighting. Okay? And this is where they get this motivation or inspiration from graph minor theory, where like they usually care about not the whole graph, but care about just some terminal vertex set. Once you want to care about only terminal vertex set, you need to do expanded decomposition based on those terminal. So that's why they need to talk about expanded decomposition for that node weighting, that set of vertex. Okay. And then they show a bunch of applications. One of the really impressive application is called grid minor theorem by Chandra Chekuri and Julia Chusoi. So maybe I tell you roughly. Good. So basically, what should I? So what is grid minor theorem? Grid minor theorem says that if maybe I skip this. You can look it up, but like that's really impressive result. Yeah. Okay. But to talk about this thing, they need to talk about vertex expansion and directed expansion. They need to talk about vertex expansion, and I will talk about vertex expansions like maybe later in class. Also, after Recce result is the algorithm by Pratasku and Thorap when they define separated expanding hierarchy. So this is a weaker than BSE hierarchy, but it's defined later. Okay. And they use it to get connectivity oracle under edge failure, the one that we saw in class. So this is like the thing that we saw in class here is actually from this paper. Okay. So basically already like around like something like in these 5 years, until 2005, during this time, both expanded decomposition, SE hierarchy, BSE hierarchy has been defined. They are there already, so it's been there for quite a while. Yeah. But they are not quite formalized in quite a unified way. For example, Pratasku Thorap defined this thing, Recce defined this thing. There are no like they don't know. They don't really actually even cite each other. So it's only become clear now that maybe that they are they are really similar to each other. And BSE hierarchy by Recke is just strengthening a strengthened version of SE hierarchy. Yeah. Right. So at least from this class, we basically see the unified way that how things in the literature are just are connected. Okay. But anyway, it was unclear why these things are good for fast algorithm. Okay. It's good. Tree flow specifier is nice. It's preserve the graph, but it takes long time to build. All this hierarchy takes long time to build during that time. Okay. So it looks like these objects looks like some object that is useful for slow algorithm when you care about graph and you can spend a lot of time. Yeah. Okay. But that changed after 2005. Yeah. After that, something changed. Yeah. But before that, I want to tell you a bit about a variant of tree-flow specifier, which is called probabilistic tree-flow specifier. So what is this? So recall that tree-flow specifier is just, tree-flow specifier of the graph with quality Q. It's just the kind of the tree whose leaf, actually, I might want to say that, yeah, the tree that span the vertex set of G, but it can have something else, right? It can have this is the vertex set of G, and the tree is have some other nodes here. Yeah. And we have that for any degree respecting demand. If D is routable in G, it's routable in T, and if it's routable in T, it's routable in G with congestion Q. That's tree-flow specifier. Now there is a probabilistic version, which is kind of weaker. Okay. So what it is, it's just that almost the same, except that it returns a distribution of trees. Okay. It's not just one tree, it's a distribution of many trees. Okay. And what's changed here is just that, okay, first, for any degree respecting demand, if D is routable in G, then D should be routable in every tree in this distribution. But the converse is that if D is routable in the average of these trees, then D should be routable in G with congestion Q. So what is this? So imagine that in my distribution, let's say that I have T1 and T2. And maybe I put a probability 0.1 and 0.9 here. Okay. So then this average of the tree in the distribution would be just T1 scaled down by this factor, union with T2 scaled down by this factor. So it's just kind of union of the two trees with some scaling. But this is to scale down the capacity of edges in this tree. Okay. So yeah. So this is so the only point that you should see is just tree-flow specifier is just stronger than the probabilistic version. Yeah.
Does that expectation thing necessarily even, like, after we take the expectation, that isn't necessarily a tree, right? Like,
Yeah, after taking expectation, this is not a tree. Yeah. No. Right. Okay. But the cool thing about this is that once you kind of allow yourself to talk about distribution of trees, then there exists the probabilistic tree flow specifier with quality log(n). And that's optimal. Like there is a lower bound of log(n), and he can achieve log(n) here. Okay. So this is kind of better than single tree version, but once it is probabilistic, then it is not enough for some application. But when you talk to people call this thing reggae tree as well. So that can be confusing because some people just know the probabilistic version, some people just know the single tree version. But yeah, so when you look in the literature, know that there are two versions that are called the same thing.
Was the tree flow specifier and the probabilistic tree flow specifier like introduced in the same paper?
No.
Oh.
Yeah, this is introduced in this paper in like 2008, but the tree flow specifier is by reggae too.
Yeah.
But
that's why I was wondering because I think I remember the name. It was like the same person.
Yeah, the same person, but this is after. Yeah. Right. But because this is like optimal, people like so it become like more famous, and then people know this thing maybe a bit more.
So the tree flow specifier quality is not optimal?
Yeah, like the best one is this thing. It's not optimal yet.
Do we know that is optimal?
We don't know.
Oh.
Like we have this lower bound, we have this upper bound.
Okay.
It's not tight. So the question is like, can we get log(n)? Or like the question for me is like, can you understand this paper and like make it easy to access, easy to understand?
are the lower bounds just existential here?
The lower is just existential. It even holds in the grid graph when the graph is a grid. So even planar graph, you need to pay log(n). Okay. Yeah, just feel free to ask questions. Today should be quite like there's no technical thing. Yeah. Okay. Good. All right. Now, there is something that I call probabilistic almost tree flow specifier. Okay. So it's something similar to probabilistic tree flow specifier, but now you allow like more complicated object instead of trees. You don't want to maybe. You allow yourself, like you used to approximate graph with trees. Now you approximate graph with something a bit more complicated than a tree. Okay. So this is the object that is almost tree is called, in literature, is called J-tree. So what is this? This is a tree. A tree which can have like n nodes. Union with a graph, any arbitrary graph now, but it only has j vertices. So think of j as small. Okay? So maybe like this is an example of j tree. When there is a core part here, the blue part, which is contain J vertex. And every other part is like looks like a tree. Like a core part, and then everything else is like a forest out of this core. Okay. Now, probabilistic J-tree flow falsifier is like what you would expect from the definition. Now it's a distribution over J-trees, and here is the same. If you're routable in the if the demand is routable in G, it's routable in every tree, in every J trees. If it's routable in the average of this, then it's routable in G. Okay. So why do people study this? Because for the tree, like even without J tree, the tree, like probabilistic tree flow falsifier is already optimal, right? Why talk about J trees? The reason is that that algorithm is slow, okay? And then we want to make it fast, okay? And so it's Madri. Okay. So Madri is like kind of before I start my PhD. Basically, he basically showed this thing, and he's the one who, like, one of the first work that improved long-standing bound for MaxFlow is by him too. Okay. So there is an algorithm for MaxFlow with this running time m root n. It has been forever, 60 years or something. And Madri is the one who first gave improvement from m root n to m to the 10^7. This is like something like 1.4 something. So that's like really impressive at that time. But now we know almost linear time. Yep. Anyway, he's now actually work at OpenAI. He quit theory, I think. Anyway, so he shows how to get this distribution of n to the little 1 tree with quality n to the little 1 in time, almost linear time. So the point of this work is that it's fast. Okay? So the quality is much worse. It's n to the little 1, still better than any polynomial. This is also like not so big, yeah, but it's fast. Okay. And the construction is not based on expander techniques that we learned in this class. There is a paper, like his paper is really easy to read, by the way. It's really nicely written. This is really nicely written. You can have a look if you want to. Okay. All right. So, okay, now back to the history. Like, basically, after this year is the year that, like, we can hope to use. It seems like expander actually is useful after all for fast algorithm. Okay. Like this one that do something fast is not based on expander. And before that, anything expander related was slow. Okay. So now, this is the 10 years that expander show impact to fast algorithms. And the first work is maybe like by Spielman and Teng. This is a work that get Gödel Prize or many other prizes, I think. But it's really super influential. So okay. The key thing that they show in their work, like the is the first expanded decomposition, like phi expanded decomposition, that whose running time is something like near linear if phi is not too small. If think of phi as 1 over log to the 1 over polylog, then this would be near linear. And right, and it's weak in some sense. It's not quite expanded decomposition exactly like we learned in class. It's a bit weaker, but it captured the spirits and it's useful enough. Okay. And so this is basically the first work that can use to approximate the expansion of G. By of G, I mean the degree node weighting of G, okay, in a linear time. And once you have that, you can use it to solve many things. Like, once you have expanded decomposition, they use it to solve something called Laplacian solver. What is Laplacian solver? Like, this is a problem where you have a linear system, and its linear system have, like, if you multiply x to this linear system, it's equals to b, and you want to find what is x. So this would be called, this is, in general, it's called linear system solver. Super important, right? Like solving linear system. And the best known algorithm for this problem is just to solve it by like computing x, which is A inverse times b. How to compute A inverse? That takes n to the omega time, which is slow. Okay. But like, so general linear system solver, people don't know fast algorithm how to solve it fast, how to do it. But Laplacian solver is basically when this A is defined from a graph in some natural way. Okay. It captures the problem when you want to solve elliptical flow in physics. That's Laplacian solver. So whenever it's basically it's a linear system solver when A is defined from graph, then it turns out that using expanded decomposition and so on, and other continuous optimization, then they can get this in nonlinear time. And once people know how to solve Laplacian solver in nonlinear time, then they use it to try to solve many other things. So really impactful. Okay. Good. Okay. But at least something about expander is now fast. Yeah. Now, in this year, Kadega, Rao, Vasirani, they talk about cut matching game. So this is 20 years ago. So this is, in this paper, is the version that we learned in class. Yeah. The one that do random projection and find the median, that thing. Right. And once you have a cut matching game, then we see in class, right, how to approximate expansion of any node weighting using MaxFlow. So what in class we see that the running times look something like MaxFlow time. MaxFlow calls, we make something like log square mini MaxFlow plus this. That's the running time. But this is the time for computing exact MaxFlow. But actually, And that's what they state in this paper too. But actually, you can use approximate Mach flow. That's good enough too. Okay. Right. Okay. Okay. Right. And yeah, it's the probabilistic tree flow specifier, the optimal one, is introduced after this. And then, yeah, 2 years later, Madri make it fast, the J3 thing. Yeah. Okay. So, but at this time, right, Mach flow is not fast yet. At this time, Mach flow, by that time, people only know Mach flow, which is this running time. Also, approximate Mach flow is just this running time. So it's not so fast yet. Yeah. But it's by this work, like 2013, when people first show that, at least not for exact, but for approximate Mach flow, they can solve it in almost linear time. And the way that they show how to solve is to basically kind of use this thing, which is fast, as a black box, and then compute Mach flow, approximate Mach flow. Yeah.
What's the approximate factor?
1 plus epsilon. So this is something like, yeah, almost linear over epsilon square. So that was like a really big breakthrough at that time. Yeah, like we didn't hope that Mach flow can be so fast, but now, at least for approximate version, is fast. Yeah. We're gonna learn this paper soon. Yeah. But okay. But then, and once approximate Mach flow is fast, then this paper show how to get tree flow specifier based on approximate Mach flow. We also learn, by the way, how to compute tree flow specifier fast in polylog Mach flow. It's basically this paper, but I just show it for I just assume exact Mach flow just to simplify the discussion. But actually, even if you allow approximate Mach flow, it just extends. Yeah. Like you need to pay a bit more. Like there is some more complication, but you can make it work. So our tree flow specifier algorithm that calls spiral Mach flow, yeah. So now it's fast. Yeah. Okay. So we just learned this algorithm like just before this lecture, right? I think so. Yeah. Okay. But what's going on now? So what's going on now is that approx Mach flow kind of reduced to tree flow specifier like if you want to solve approx Mach flow, actually no, reduce to probabilistic. Even the probabilistic version is enough to get approx Mach flow fast. This is just here, right? This is like it reduce approx Mach flow to probabilistic tree flow specifier. But tree flow specifier here is also reduced to approx Mach flow. So there's like this Actually, maybe I should say this. Probabilistic J3 flow falsifier. Okay. If you want to solve this, like this thing shows this one. Okay. And to get 3-fold falsifier, it's now enough to just use approximate flow. But if you want to solve approximate J3 flow falsifier, clearly this is weaker than 3-flow falsifier because this is a single tree version and it's 3. This is weaker, it's probabilistic and J3. So you see that there are like this circle of dependency and everything, but because like but this thing because you can solve this in almost linear time, then you can solve this in almost linear time, and you can solve this in almost linear time. But then, like, it's by Richard Peng that observed this, like, cyclic dependency, and then he, instead of using this one as a black box, which takes like almost linear time, he basically showed how to get just nonlinear time for both of this actually, for both this and this. And the way that he do is like to kind of just to solve this, just solve this, to solve this, just solve this. But so, like there is some circle, like a chicken and egg scenario, but he resolved this using something called, he used something called ultra, like maybe I should say J3 falsifier. So J3 kind of just is still there, but it's used inside the recursion, and he can improve the running time on both of these. Yeah. Okay. Anyway, it's like his interesting history that the way how to get fast approximate Mach flow is just to solve 3-flow falsifier and use this recursion. Okay, but anyway, like now it's kind of clear that 10 years after Spielman and Teng, it's clear that expander are kind of powerful for fast algorithm. Yeah. Like you can solve 3-flow falsifier fast. Also, approximate Mach flow is now fast. Yeah. Okay. And after this year, until now, in last 10 years, like expander-based technique has been hugely extended in 2 ways. One is that it now has impact across many models of computation. Another is that it has been extended to other notion of expansions. Okay. So I tell you roughly on both. Okay. So first, across model of computation. So okay, there will be like just classical static model, and then dynamic algorithms and distributed algorithms. So first, for the static one. Okay. So there are like some work that try to improve the core object itself. It started by Spielman and Teng, right? Long time ago. But then I and my co-author basically tried to get fast expanded decomposition, like not the weak one, but the one that we learned. Yeah. And the first almost linear time is here. And then we make it faster and simple. Like, we didn't learn this one, but we basically kind of learned this one. The one that, like, how to compute expanded decomposition using spherical Sumac flow, like polylocal Sumac flow, is basically this algorithm. But in class, I just show how to use black box Mac flow. There is a way to not use black box Mac flow, which we will learn next. It will use push relabel algorithm instead. And we see this algorithm soon. Yeah. Okay. So like, now expanded decomposition is fast. It's actually even near linear. But they are all randomized. But we we also try to make it deterministic too, and we did. We get deterministic expanded decomposition and fast. And how did we do it? Well, we look at cut matching game and we make it deterministic. Okay. So in the last homework, like in the last question in the current homework, you see how to get deterministic cut matching game, but the slow version. There is once you learn this, we do the same thing, like to get cut matching game, deterministic. It's enough to find balanced sparse cut or get giant expanding set. This is like the core subroutine that we want, right? Find either balanced sparse cut or say that the complement of the cut is an expanding set. And the deterministic version of cut matching game just asks you to solve this one. But you also know that to solve this problem, we need cut matching game. If one way to solve this problem is to solve cut matching game. So there is this chicken and egg dependency. The one that you learn, if you solve the homework, you learn like the algorithm that is slow here. But once you learn this chicken and egg dependency, you can resolve this one just by recursing on top of each other and make everything fast. So this is kind of the theme in the area too, like that when you see how to solve one problem by reducing to each other, then there might be a way to just make both of them fast. Yeah. And this is what we did here. Once you have fast deterministic cut matching game, you get deterministic expanded decomposition. You can see this because if I can solve this thing fast, if I can either find balanced sparse cut or giant expanding set fast deterministically, then you see, right, that we can just compute expanded decomposition fast. How? Just call this thing. And if you get balanced sparse cut, recurse on both sides. Otherwise, you get small cut, but everything else is expanding, just recurse on the small side. So everything is deterministic once you have this one. Okay. And once expander decomposition is deterministic, then like all the previous application of expanded decomposition become deterministic, like Laplacian solver, other specifier, and a bunch of dynamic algorithms. But yeah, okay. Our algorithm is almost linear, but not nonlinear. And it's a big open problem if you can make it nonlinear. So, because once you can do it, then basically you could just gonna speed up bunch of deterministic algorithm. Okay. All right. But like the impact of expanded decomposition is not just this. So we see that, okay, you can get approximate max flow, but there are many other applications actually. Like one is to compute global min cut. So what is this problem? It's really just like you have a graph, you ask how many edges you need to delete just to disconnect the graph, just to make the graph disconnected. So you don't talk about like fix S and T and try to disconnect S and T. You just delete. You ask like to disconnect some pair. Yeah. So that's global min cut problem. And there is like impressive work by Kawarabashi and Thorap. This get focus and price, and then a bunch of works by Jason Lee. The L here is Jason Lee. And this one just get the best soda paper. And yeah, they make like, it's like this problem, like 20 years ago, like in 2000, Karger shows how to solve it in nonlinear time, but randomized. But his algorithm is really randomized. It's hard to imagine how to make it deterministic. And then it's actually by using something like expanded decomposition that they managed to make it deterministic. So that's one cool thing. And there are other things like connectivity, labeling scheme, and parallel algorithm, which I will not talk about. But the cool thing is that it turns out that we see how approximate max flow can be solved using expanded decomposition. But it turns out even exact max flow is benefited. Like you can solve it using expanded stuff too. I talk about it soon. Because actually to get this, it's actually through dynamic version of expander stuff. So let's talk about dynamic thing. What's dynamic graph problems? Well, it's just a problem where you have a graph and then you have some sequence of updates. Like you have a graph, you insert an edge, you delete an edge, and you can ask all kind of things. You ask to maintain minimum spanning trees in the graph, or you can ask like if U and V is still connected in the graph, what's the distance between U and V, and so on, right? So it's a really natural question to ask. Like, it's not just enough to just solve some problem and you're done, because the graph in our everyday life just keep changing all the time, and you don't want to just, and the graph is huge too. So once the graph change a bit, you don't want to just spend the whole linear time from scratch. You want to spend sublinear time per change. Right? So that's like, yeah.
Have we seen any examples of dynamic algorithms in this class other than the dynamic expander decomposition?
So I don't think so. Like what we see, like kind of almost dynamic is connectivity oracle
Oh, yeah.
under failure,
Yeah.
where like you spend some time and there is like one batch of updates. So that's not quite dynamic because there is only one batch of updates. We're gonna see it in next class.
And is this different from online algorithms because it's different or it's
So yeah, very good question. So both online algorithm and dynamic and streaming, online algorithm, dynamic algorithm, streaming algorithm, they are kind of in the same setting where you have an input and there are some sequence of updates that's given to you. But the difference is like the focus on what to optimize. For dynamic, you optimize time, the update time. For streaming, you optimize space. And for online, you usually optimize approximation ratio. Approx ratio.
But the setup is the same for all three of these?
So the setup here is basically it's really the same. The online one usually have one more constraint. That is cannot revoke previous decision. So like you see online multi-cut or online set cover, once you decide to cut something, then it is cut forever. But maybe for dynamic or streaming one, you can imagine online like dynamic multi-cut problem where you want to maintain a multi-cut solution at all time, but the thing that you decide to cut you might decide not to cut after that. So yeah, so that's kind of the difference, but they are kind of related, and many times like some techniques in these three areas sometimes just transfer. Yeah. Like once you kind of identify like the core object that is useful for dynamic, sometimes it's just useful for this thing too and this thing. Yeah. Because in some sense, they kind of address the same thing. That is, they address robustness. They address uncertainty of the future. Yeah. Okay. Good. Yeah, but here, like, yeah, the goal for dynamic is to get fast update time. Yeah. Ideally, polylog time. And you see this thing, which is the Bratton-Thorap connectivity oracle that we learned in class. And like this is kind of almost dynamic because it's not quite dynamic because it only handles one batch of updates. But this is like this connectivity oracle is like one application of expanders to almost dynamic setting. But then in this work, we show dynamic expanded decomposition when the node weighting is degree. If the node weighting is not degree, node weighting, we don't know. We don't know dynamic expanded decomposition. So recall that to get BSE hierarchy, we need dynamic expanded decomposition, but that construction, the node weighting is not degree. Okay? So we have a fast algorithm for when the node weighting is the degree. But to get BSE hierarchy, we need something more. Okay. So this is fast. And this gives like several applications. Actually, what we show is like a dynamic MST, dynamic minimum spanning tree, with like a enter little one update time. So improve from root n to enter little one. And then so later we show dynamic tree flow specifier. Yeah. This is the and how do we get this? We use BSE hierarchy. Dynamic BSE hierarchy. What's the version of this one? It's the one that we, compute boundary link, expanded decomposition, and contract. That's the version that you learned, and it can be extended to dynamic version. Yeah. Okay. And then a few years later, like last few years, there are just so many dynamic algorithms that use expanders. So it really become clear that expander is just super useful for dynamic algorithms. And so like basically all kind of things like minimum spanning tree, KH connectivity, approximate flow, and so on. Like they are based on expander and other stuff. Yeah. So, but everything here rely on something that I call expanded pruning. We're gonna see what this is. But it's just, the idea is that you have this intuition already that expanders are robust under updates, under edge failure. This is, the intuition here is there when you learn about connectivity oracle. But we're gonna kind of push that to the limit. Yeah? And you see this, you learn about this. But let me tell you roughly for now. Okay. So you know that expander are robust under updates, in the sense that if it's not expander, then when you delete a bit, you get a big change. If it's expander, if you delete around here, you can only disconnect things around here. If you delete like something else, it doesn't even disconnect. So basically, small change, like small number of updates, implies small change. That's how expander is. But expanded pruning will do the following. Like, imagine that you start with expander. Then suppose that I delete some edge. This is like I delete some edge here. Then what it will do is like it will find you a set to prune out, P1, such that the complement, like GI, when you remove the prune set, this set, this thing is still an expander. Okay. And then the next update may come. You might insert or delete, whatever. The algorithm will update the prune set to P2. And the rest, this set will grow a bit, and the rest is still an expander, and so on. Okay, so specifically, like the algorithm will maintain the vertex set P, such that this P grows really slowly. After I update the set P, we have like degree, the total degree around I times polylog. And by expander here, I mean like degree G is 1 over, let's say, log expanding. Yeah. And the update time to compute from pi minus 1 to pi is just polylog time. So like this is kind of strong in the sense that any question about this statement? Like you see that like kind of each update. Like normally, like when you have expander, if you just delete a bunch, you know that you're gonna disconnect not too many, and the rest here is connected. This is connected. There's a giant connected component. But what this thing shows is that you can show something stronger, that this is not just even connected. It's an expander. It's robustly connected on the complement, not just connected. Okay. And each update will only like cause small problem. The prune set that you need to prune out is small. And the remaining part is still an expander, the thing that is good for you. So once you kind of, because expander is really algorithmically friendly, things on expander is nice. And now that you have this, which shows that after updates, you really kind of still have big expander at all time. After you have big expander at all time, it keeps shrinking by only small amount after each update. Once you have this, then you kind of combine these two things. It's friendly and it's robust, so you can solve anything under updates.
Are we removing vertex each time, or
Are we what?
are we removing vertices each time?
Yeah, removing vertices.
Or the EI are like vertices or edges.
Oh, sorry. This is edge. Yeah, this is edge. This is edge update. But the set P is a set of vertices.
Oh. So we can add or remove edges.
Yeah.
Does this run into problems with like too many deletions or something?
Right. So first of all, let's say that if I equals to M, then this can be as big as M. So you would say you prune everything. Yeah. So this statement makes sense only when like number of updates is not too big.
We're assuming GI is connected here.
We assume GI is connected. Yeah, like connected expander. Yeah, you will. I hope to tell you how to solve this thing. Once you learn about push level. Okay. But so you see that like this is an intuition why like you expect that the expander are just really useful for dynamic algorithm. It's friendly and it's robust. So you solve a bunch of things. But it turns out that the fact that you can get dynamic expander stuff efficiently, it turns out to be a key tool for the really big breakthrough in the past few years. Okay. So okay, I told you that like once we learn how to solve approximate max flow 10 years ago or so, like it was really amazing. People celebrate. But now we know how to solve exact max flow in almost linear time. Okay, so that is really big, at least to many algorithm people. Okay. But it's good to know that these all modern max flow algorithm, they kind of exploit or use something about dynamic algorithm for expanders. like the tools that you learn here is actually the core thing inside this. So before we know almost linear time algorithm for Maxflow, there is this work that gives you kind of near linear time when the graph is dense enough. Okay. But what it uses is like some kind of dynamic specifier. This is basically the edge specifier that you learn in this class when you compute repeated expander decomposition and specify each expander. That same algorithm don't just preserve cuts, but preserve spectral guarantees actually. And it works in the dynamic version. So it's useful for this one. And then there is this work that a really big breakthrough of almost linear time Maxflow. And it used this dynamic spanner. But actually there is the new algorithm that don't use expander at all actually. So maybe I shouldn't say all. There's one new paper that use dynamic spanner but don't use the dynamic expander stuff. But then there is another one which use dynamic tree flow specifier. And it's maybe the simplest one to learn among all this. Yeah. So if you want to learn how to compute Maxflow fast, just learn from this paper. And what's like open is that dynamic tree flow specifier that in this work. Yeah. Okay, maybe I just ask. If you have dynamic tree flow specifier with quality polylog and update time polylog, you would just improve this algorithm from almost linear to near linear. So what they use here, so if you recall, I developed this dynamic tree flow specifier with quality nt-1 and nt-1 update time. They just use that and they get this thing. But if you can improve this to polylog, then you basically achieve the real like holy grail of flow algorithm. So that's like, it's really interesting if you can do this. I really want to know. Okay, good. So you see that this development of expanded stuff is useful in static. And then we find a bunch of useful things in dynamic algorithm. And then the dynamic stuff turns out to be useful again for static thing. Yeah. And that's kind of expected because what's the point of dynamic data structure? Usually it's just used as a subroutine inside static algorithm. So, okay, good. Okay, let me quickly talk about distributed algorithm. I'm not sure you have heard about this at all, but I'll let you know a bit. So, like there is the distributed model of computation called congest model, congest setting, where like imagine that you have a graph of network. This is like network of computer, where like each node is a computer, each edge is like a connection between computer. And there is like each computer can only talk locally. It can only talk to their neighbor. Each node can send message only to its neighbor in each round. And but the message can have size like just login, which is expected. Like you want to send you can send just one number in each round. You don't allow to send like the whole database of everything in one round. That's not realistic. Okay, and the goal usually is just to solve something about this network itself, and so that you minimize the number of rounds. For example, you can ask, what's the distance from node 1 to node 4? How many hops you need to do? Or like what's the min cut of this? Where is the bottleneck in this network? How many rounds you need to communicate to each other so that you know that information. Like it's quite a natural model, like just message passing model. Now there is like some other model that is not so natural, but people look at it. It's called congested click model, which is just stronger. It's stronger in what sense? Now instead of local communication, you now actually allow all-to-all communication. So a node can send a message to everyone in one round, even if they don't have an edge to each other. So I would, for example, allow 1 and 4 to talk to each other, even if in the underlying network there is no edge. That's called congested click. So you understand this two model, right? It's just, one is just stronger. Okay. And so people ask about like a problem called listing triangle. So you have a graph and you just check, like you want to list all the triangle in the graph. Okay. Triangle is like some kind of cluster or anyway, it's like natural thing. Yeah. And in congest, which is harder to get algorithm, people get this running time. It's sublinear round. But in congested click, they get this optimal bound. Like they can prove this is optimal. It's n to the 1/3. Yeah. And that's expected because congested click is just easier to solve things. We can communicate more. But then it turns out that with expanded decomposition, then you can make it fast. Basically match the time for congested click. Yeah. And it uses both expanded decomposition and something called expanded routing. Okay. So the point is that this technique is also useful to basically kind of transfer strong result from congested click to congest. That's the message. Okay. So I will talk about expanded routing soon, but or now? Okay, now, yeah. What is this? It's a simple problem, super simple problem. You have connected expander graph, like this, and then you have some demand that respect the degree, and you want to route this demand, basically. But this demand should be short. Like the flow here should be short. Each flow path have length, let's say at most q, and the congestion of the flow is small. Okay. Think of q as something like n to the little 1. So that's it. That's expander routing. Just routing on expander. Okay. And what's known is that when the quality is n to the little 1, we have an algorithm. There is an algorithm that is like almost linear time. And what's open is that can you get polylog? And it turns out to be super important again, like a bunch of things really just rely on this thing. Okay. And it's super natural problem. Like you have expander, route the demand on expander. How can you do that fast? And why expander routing is useful? Well, like, okay, I don't have time to do this, but okay. So it basically kind of like any node can basically now. So think like this. Suppose that your graph is an expander. And if you want to do expander routing, it basically allows you to chat to exchange message to any node, any other node with small number of routes because the flow is short. Okay. So it's kind of, you see that the intuition is that it now simulates how to do all-to-all communication instead of local communication. Yeah. Like expander routing allow all-to-all communication similar to congested click. That's the intuition. So if you can do this fast, then you basically can simulate congested click model. Okay. All right. So we will so that's just like development across many model of computation. And later in class, we will talk more about development to other notion of expansion. Specifically, we will talk much more about directed expander. Yeah. Okay. Questions? Okay, then yeah. So I hope you guys come to the class tomorrow so that we talk about project. And next week, we will start looking at push reliable and dynamic shortest path, how they are actually related. Like this is quite cool because people talk about dynamic shortest path and push reliable separately. I'm gonna present it in the unified way. Like they are kind of the same thing. And you'll see next week. Yeah. All right, so that's it for today.